I'd like to close now with a final third example, which begins to get us into questions of energy. We've seen how to analyze these circuits, just like we had with capacitors. But the other nice thing we understood about capacitors was energy and its relation to capacitors. So let's think a little bit about energy and inductors. So here's what my example is going to look like. It's going to be the simplest possible LR circuit. In particular, all that I'm going to have in this circuit is some resistance R on one side of my circuit and an inductor L on the other side of my circuit. Now what's going to make this circuit at least interesting is I'm going to have, by somehow or other, perhaps using the circuit that I'd shown you previously with a battery in there, I've somehow or other powered up this inductor L. And then somehow I throw a switch which brings the power source out of the circuit. But the key thing is that at the initial moment when this circuit is set up, I'm going to have some current I that's actually already flowing through my inductor. And the question is going to be twofold. One is, what happens in this situation? And the second one relates to issues having to do with energy. So let's at least give a sketch of what we expect to happen in this system. Now, if I sketch the current, in this case, as a function of time t, from what we've just said, before t equals 0, I had some battery or something in this circuit, so there was some initial value for the current coming in here. I'll call that I naught. Now, we know now that the second we've switched the circuit out, like I've done here, the current can't stop flowing. It has to be continuous at time t equals 0. We can expect, though, that it's going to want to decay away. And in fact, as time t goes to infinity, using our rule that we can, at steady state, replace inductors with wires, I just have a resistor with a wire. I know the current has to be 0 out at infinity. So it has to want to drop, and then it's going to have to approach 0 as I go out towards infinity. So some kind of exponential decay here is, again, the type of thing that I'm expecting. Now, I just want to be clear. I don't want to mislead you guys here. The initial current was going to be constant coming in here. I didn't want it to have a tilt like that. All right. So this is very fascinating because the current keeps flowing even when there's no battery in the circuit. But when current flows through a resistor, we know, for instance, the resistor is heating up, right? There's some source of energy in this system. But it looks like all there is here really are just some wires. So there must be some sense in which energy is stored up in this inductor once it's powered up with this current I flowing, because there's always this potential for continuing to drive that current through a resistor and to drive a load in my circuit. Very well. So let's try then to see how we would analyze such a circuit. We can expect right away, since I only have two circuit elements, it's pretty simple that I'm going to have the same current I flowing through both elements. So I won't bother with K1. But let's look at our effective Kirchhoff's second law. And in this case, again, we have a presumed direction for the flow of current. So I should label the upstream and downstream sides of my inductor as the current flows through it. And similarly for my resistor, as the current flows through it. And now I'll take my Kirchhoff loop through my resistor. I'll use this as my starting and stopping point. And this time I won't be so perverse. I will actually loop around in the same direction of the current as the current. And if I do this, Kirchhoff's second law, effective second law, says 0 will be the sum of the effective voltages. The first voltage I encounter is my resistor with a current I flowing through it. But I am going now with the current. I am going downstream from plus to minus, so this enters with a negative sign. The inductor then is a very similar story. It's plus or minus. The inductor formula is L di dt. And once again, I'm going around this direction. I'm going from the labeled plus to the labeled minus side of my inductor. I'm going downstream. I'm going with the flow of the current. So in that case also, by the same mnemonic, that enters with a negative sign. So I can put all this together then, and I can see what's going to happen in my resistor. I will find that IR, by moving this to the other side of the equation, equals minus L times di dt. All right, very good. And now I have an equation I can solve, and if you solve this, we will spare you the details, but if you solve this, you can use separation of variables if you like. You will find a nice, simple exponential decay, as we've indicated here. But now, let's think about energy. Let's think about conservation of energy. Now, if we believe in conservation of energy, which we certainly do, right, then we know that the power that's coming out of this circuit, right, it's going into mechanical power, or in fact, in this case, it's going into heat, has to be exactly accountable by the time derivative of the changes of stored energy in this system. And in this system, the only other device besides the resistor, which we know is dissipating the power, the only other device is the inductor. So there must be energy somehow stored in this inductor. So let me call that the energy in the inductor. Now, always with these accounting things, in this course I emphasize, it's always either plus or minus, and we have to be careful with our signs. Now, clearly here, as time goes on, I'm dissipating power. So the power out is going to be positive. It's coming out as heat. And if this is positive, I know that if I'm dissipating power, the energy stored must be decreasing. So du dt would have to be negative, and for this equation to give me a positive power out, clearly I have to choose that negative sign. Now here's the trick. I want to relate this to what I know about the physics of resistors and inductors. So let's see. The power out, I know from a resistor, is always the current flowing through the system times the resistance. And I'd like to relate this to what I just wrote about the inductor. So let me write this as I times IR, which of course, if you recall, that just means it's I times V, another famous power formula. But the advantage of writing it this way is I know what IR is. I can substitute this in here for IR, and then what I will find is I times minus L di dt. Or if I rewrite this just slightly, it's equal to minus L times I times di dt. So I have a nice, neat relationship between change in stored energy in the inductor and the changes in the current. So let me rewrite this just a little bit. If I believe in conservation of energy, this term must equal that term. So the time derivative of energy stored in the inductor, which had a minus sign on it, is going to equal minus L from this side of the equation, I times di dt. But of course, it's a little silly to write both minus signs. I can multiply through by minus 1. So now I think I can understand the energy stored in the inductor. It's some function whose time derivative is L times I times the derivative of I. Well, this is some kind of differential equation to solve. And we know the method for solving differential equations. The real method, of course, always is you just guess. So I have to guess at what derivative would give me back L. Well, I'm sure L is just a constant, so I can write L times I times the derivative of I. Well, that sounds a lot like the chain rule. It sounds a lot like the derivative of I squared. Let's test that. If I take the derivative of this with respect to time t, I will get L. That's good. I'll get a factor of 2. Oh, I don't want a factor of 2, so I better put a half. Now I won't get a factor of 2, but I'll get I back, and then I need the time derivative of I by the chain rule, so this equation works. The only missing issue is that I've integrated, so there can be, of course, some unknown integration constant, C. But I think it's pretty clear that if there were no current flowing through my inductor, right, if that were zero current initially, there's no way, I mean, the current would just never change, right? I would just have like a dead circuit sitting there, and there'd be no chance to get any energy out. So I know that the energy has to be zero when the current is zero. And that tells me that any integration constant here itself actually would have to have the value zero. So we have a very nice result now, and we can understand exactly energy storage in inductors, that it is related to the square of the current. And what we'll try to explore next time is, where is that energy actually stored?